Okay, so, hi. This seems so weird. I have like 3 feet to move in, and I'm used to having so much more room to move in the lecture hall, but I'll just have to suck it up and deal with it. If you can't see what the hell I'm writing on my board, just let me know, and I'll try and reshift the position of the computer and the angle and everything. And as I pointed out to, I think, Gabriel, the lighting for the computer sucks, but the lighting for the camera is good. So I don't know. I might just end up going to campus and going to an empty classroom and teaching the real way, but I'll try this first, okay? All right, let me know if you can't see this, what I'm about to write on the board, and then I'll either write bigger or something, okay? So, well, I can reach the top. That's pretty cool. So I want you to recall, for starters, the ABCs, okay? This is what we learned. Can you guys see that? If you blow me up and pin me and make me your, because I'm only seeing my tile, which is tiny. So I have no idea what it looks like, but you can see it. Okay, good. Okay, so last time we talked about the Feynman rules associated with this particular theory, whose Lagrangian I'm going to write down in just a moment. And what we're going to do today is we're going to start by me kind of giving you a means of looking at a Lagrangian and from the Lagrangian pulling out the steps in the Feynman process for that theory. In order to truly derive this, you would have to do quantum field theory, which is that's beyond the level of this course. We're not going to do it. So I'm just going to give you the rules, but we're going to kind of at least get them from the terms in the Lagrangian. And that's good news because a Lagrangian is the definition of at least a classical version of a theory. So it kind of contains all of the starting point and all of the theory information that you would expect in the quantum version. So let me remind you of the Lagrangian for the ABC theory. And Avery, now is an appropriate time to tell a joke. Avery.
I don't want to tell the jokes that I'm thinking of. Do it. We got Scooby-Doo here. Shut up.
I guess these should have A, B's, and C's. I'm putting subscripts on the M's because all those fields might have different masses. And then we have this really badass last term, which is the interaction in our theory. Okay? So just a very quick reminder of what we did last time, and we went through some examples of applying this. So what we discovered is that, first of all, we built all of our diagrams out of lines that basically represent the propagation of particles A, or fluctuations A, B, or C, okay? And then to complete a diagram, these lines had to intersect, and that intersection in this particular theory was just an intersection vertex with 3 operators, and they're all different. Okay, this obviously comes from this term because it's the interaction of all 3 fields. Notice we don't have a vertex where it's AAC. We would if there was another term in here, or sorry, phi A, phi C, phi A. If we had this term, then we would have a vertex like that, but in our original version of this, we don't have that, so we're not going to worry about it. Okay? And then we used minus IG for each vertex that appeared in the diagram. And then we used a factor of I over Q J squared minus the mass of the particle in question squared times C squared. And these are virtual particle propagators. Okay, now I just threw these at you. I didn't give you a methodology for how to get these terms that we write down from the Lagrangian, and that's what I'm going to do now. Now when I do it for this ABC theory, it's almost going to look trivial, because this is largely a trivial theory. But clearly what we're going to turn to next today is we're going to throw spin in it, which we have to do because the standard model is not based on interactions of scalar particles. It's really based on fermions interacting with vector bosons. So I'm going to, first of all, just give you an idea of how we take the Lagrangian and we extract these factors, and then we'll turn it over to the spinor version. Okay? So if you want to get vertex factors, all you do is you write I times the interaction term in the Lagrangian. So this is the interaction term. We'll just call it L interaction. So you write I times L interaction in momentum space. So what that of course means is that we replace I h bar d mu with p mu wherever we see it, or of course we can just replace the derivative with minus I over h bar p mu. Okay? And then you erase the field variables. So let's see how this works out in this ABC example. If I take this interaction term and I multiply it by I, and then I take all of the derivatives that appear and send them to this, well, what does it do to this term? Let me pick a card. Joseph! Where the hell are you, Joseph?
I'm here.
You're here. Joseph, what is this term going to become when we multiply it by I and then replace the derivatives with these momentum terms?
Well, we don't have any derivatives in that term, so we just multiply it by I.
Bam! See? It's not that hard, is it? It's pretty damn easy, okay? So we're going to have minus I times G phi A, phi B, phi C. Okay? This is clearly going to not be as trivial when we're doing quantum electrodynamics, but in this case it turns out to be pretty trivial. Now, the next step is to erase the field variables. Stephen, are you on? Stephen is. Stephen, what are the field variables in this? Well, actually, we'll point to this now. What are the field variables that you see in this term?
None, because they're scalars?
Fields can be scalars. Fields can be scalars.
So A, B, and C?
Yeah, so you erase phi A, phi B, and phi C, and that leaves you with minus IG. That's exactly what we said you put in every time you see a vertex in this theory. You see me pointing at this? That's what I just derived. Okay? So these are the steps of how we're going to get the quantity that we write down every time we see a vertex in a theory. And again, it's going to get way more complicated when we're doing quantum electrodynamics, but this part of the procedure is the same. Okay? All right, now propagators. So what you want to do is you want to write the free particle propagator, or sorry, the free particle equation of motion. in momentum space? Now let me remind you, a propagator term is what you write down when you've got a diagram, say like this. And you write down this term for all of the virtual particles that appear. So in this case, how many virtual particles are in this diagram? Anybody can answer it. How many virtual particles are in this diagram? One. It's the particle C. The external legs of a diagram are always the real particles. These are the ones that we send in, and these are the ones that we detect coming out. Anything which begins and ends on a vertex is a virtual particle. And so when you're evaluating, and I realize it's been more than 2 weeks ago that you guys worked with this, so that's fine. I'll try and remind you as best I can. But when you're trying to write down the expression for M from this diagram, you have two vertices, so you put down two factors of minus IG, and then you have one internal virtual particle, so you write down one factor of this, and of course, since this is particle C, you would use mass C there, and you would, you can label this Q whatever way you want. Okay, so I want to derive this, so we're going to take, if this is particle C, we want to write down the free particle equation of motion in momentum space. Now, what kind of particle is this in this theory? Anthony. Anthony, are you there? I know you're there. Yeah.
Yeah, I'm here.
Okay, good. What kind of particle is this? C. Spinor, scalar, or vector?
Scalar.
Yeah, it's a scalar. This ABC theory is built from scalars. You can tell by kind of looking at the kinetic term in the Lagrangian. So what is the equation of motion that governs a free scalar? It's either the Klein-Gordon, the Dirac, or the Proko.
The Klein-Gordon?
Yes, yes, it's the Klein-Gordon. It's the Klein-Gordon. So we write down the Klein-Gordon equation. Okay, so that's the Klein-Gordon equation, but we want to put it in momentum space. So we again do this replacement of all derivatives with minus I over h bar p mu. So this is going to become p squared minus mc squared all on phi. And there's one more step here, and lose h bar. Okay, so if you just plug in the d mu goes to minus I over h bar p mu here, you're going to get a 1 over h bar squared, but you want to eliminate the h bars. So just get rid of them. Okay, and again, what I'm saying to you might sound like, oh, why is he doing that shit? You know, you could derive all this in quantum field theory, we can't derive it. So you got to take these as steps that you just have to follow. And get rid of h bar is pretty straightforward. When you put in the d mu as I over h bar p mu, this is going to give you a 1 over h bar squared, which has got the same dimensionality as that, so you can erase it from both sides. Okay, now here's the hard part. This is going to be even harder when we're doing spinners, okay? Next, you want to multiply the inverse of the term in brackets by I. Okay? Well, look at the term in brackets, p squared minus mc squared. What is the inverse of that? Anyone? Avery, if you're saying it, you're still muted.
Oh, 1 over that.
Yeah, it's not that hard, folks. And then you multiply it by I. Doesn't that look familiar? Yeah, I know. It's funny. Your reactions, I'm used to like your reactions having noise associated with them, but you're all sitting there with your mics off, and so Sarah's like, but it's completely quiet, and she's clapping, and it's quiet. It's weird.
You want us to unmute ourselves so you can feel better about it?
Yeah, no. I don't know what kind of cacophony of noise we would get if you all unmuted. Oh, actually, everybody unmute for a second. Let's see how loud it is.
If we all unmute and shake our heads, you can probably hear the brain rattle.
All right, do it. Do it.
I mean, like if my birds start squawking again, then I'll mute. Like,
Just ignore the gunshot.
Gabriel, did you swallow water bottle?
Okay, all right.
No, I don't even deep throat this water bottle.
Okay, okay, okay. All right, I'm gonna get back to this.
Such a good idea.
Okay, so are there any questions about this before we turn to Dirac and spinors? Seem pretty reasonable? Okay, and again, if you ever want to see this derived, you're going to have to take a course in quantum field theory. Oh boy. I don't know what's going on there. I don't know what's going on there either. Okay. Oh Lord. This whiteboard sucks, but it's what I got. It's what I got. Okay, here we go. Whose house? Dirac's house. So we're going to take this and we are going to now transition it to the basic of the quantum field theories that are applicable. I want you to consider the QED Lagrangian. That's quantum electrodynamics. So let me write L up here. L is I, H bar C. And I want to go ahead and tell you that you might or might not remember, but when we moved into this part of the course, which is very specifically particle physics oriented, we made a couple of convention changes. Our metric tensor is now 1, minus 1, minus 1, minus 1. There's different bases that are often used for the Dirac matrices, and there's some shifts in some of the equations of motion. Okay, everything I write, I'm just saying, like, don't take the Lagrangian that I gave you early in the semester for quantum electrodynamics when we were deriving it from a local U1 gauge invariance. It's gonna, some coefficients are gonna look a little bit different, but I want to try and make this as close as possible to the resources you can look at for this material. Avery, you really need to have a joke.
Is there a way so I can have it so only Dr. Floyd's screen done?
Yes.
If you click on this video, you can video.
Yeah. But I click on what?
You click on the dots up the upper right hand corner of your picture, and then you pin me.
Yeah, okay.
You pin the video. Okay.
My red book.
You forgot your red book?
Oh, found it.
Oh, good. Oh, good. Good. That's excellent. Weird. Okay. All right. So let's think about this for a moment. What do you think the fundamental vertex of interaction in this theory looks like? And let's take Brandon. Brandon, are you there?
Yeah, I'm here.
Yeah, good.
Last lecture's a little bit behind.
Say it again.
I missed the last lecture, I'm just a little bit behind, so I'm confused.
Well, that's fine. So, so this is actually hearkening back not to the last lecture, but to when we derived interactions from local gauge invariants. So this has a psi bar and a psi, so it's a kinetic term. This has a psi bar and a psi, this is the mass term. This has psi bar, psi, and A. Is that an interaction?
Yes.
Yeah, it is. And so you can probably guess what that vertex would look like. It would have three factors. It would have one associated with psi bar, one associated with psi, and one associated with A mu. And so if we draw it, it looks like this. Okay? So this is the fundamental vertex from which we have to build all of the diagrams that we're going to use to connect a set of in states with a set of out states. Okay? It is a particle coming in this case I chose an electron, but you could really pick any of the spin-and-a-half particles. You could pick quarks, you could pick leptons, except not neutrinos, because neutrinos don't have electric charge. But the electron comes in, the electron goes out, and the photon comes in or out of the thing. And I'll explain why there's arrows on some of this and not on some of it in a bit. Okay? Now, so how do we get the vertex factor associated with this? So what's the first thing we do to get the vertex factor associated with this vertex in a picture? I just showed you what to do for ABC. Let's apply it here. Sean, are you there?
Yeah.
Sean, what's the first step in getting the vertex factor that we would write down associated with that vertex appearing in our diagram?
I'm not sure. I'm reading through Lagrangian. I'm not sure. I really don't know.
Okay, you can phone a friend if you want, or you can just wave and maybe somebody will wave back. Anybody gonna help him? Joel?
So don't you multiply the Fourier transform of the interaction part by I?
Yeah. Well, we'll do the Fourier transform of this in just a moment, but the first thing you do is you grab the interaction term in the Lagrangian and you multiply it by I. Okay? So now we're going to have minus I q psi bar gamma mu d mu, or sorry, psi a mu. Now, are there any derivatives that appear in there? Do you see a derivative in that term?
I don't think so.
Yeah, there's no derivative in that term. Okay? So if we're going to send this to a Fourier transform, we don't actually have to do anything to it. Okay? So then what's the next step that we have to do?
Don't we get rid of all the fields?
Yes, we erase the fields. What are the fields that you see in here?
I see a psi bar B. And I think, I can't really tell, but that's a gamma, not the B.
Yeah, that's a gamma mu. It's contracted with the A mu.
I really just can't tell.
Okay, so I would say that psi bar is a field, psi is a field, and A mu is a field. You know, if you look up here, this is a kinetic term for the spinors, psi and psi bar. So psi and psi bar are fields. D mu is just a derivative operator acting on it, and gamma mu is just a gamma matrix. It's not a field.
Yeah.
So look, if I were really like notationally crazy, I would take, you know, this term and I would write it like this. I would say this is IH bar C psi bar, which is a function of where you are, times gamma mu times D mu times psi, which is a function of where you are. And anytime something's written as a function of where you are, that's what a field is. A field is a function defined throughout space and time. Okay? So if I wrote it like this, it would be obvious that psi and psi bar are the fields, but I can't keep doing this. This is way too much to write. So in looking at this, you know, Q is the charge, so that's not a field. Psi bar is a field. Gamma mu is not a field. Psi is a field. A mu is a field. Okay? So we're going to erase psi bar, psi, and a mu, and that's going to leave us with minus IQ gamma mu. Okay? That makes sense?
Yeah, it was just really small and hard to read.
It's, do you have me pinned so you can see the big version of this?
Yeah, it's just, I couldn't tell what any of the symbols were.
Okay.
It's a little blurry based on you streaming it.
It's, sorry, say it again?
It's just a little blurry, like the video connection is
Like
not
frame.
really.
Yeah, it's not a high quality camera, so
Yeah.
it's
If you maybe like just slightly bigger.
Slightly big.
The actual variables. I just can't read the subscripts. That's my problem.
It should be in one color, so it's kind of hard to pick anything.
Okay.
There should be an option in Zoom video to enable HD.
To do what?
To enable HD, it's in the settings for video on Zoom.
Yeah, but can I fix that now, or do I have to fix it later when I'm not in a
I think
presentation?
you can fix it now.
Oh yeah, you can. So if you go to the little arrow next to stop video, and then go to video settings, dot.
Hold on, so the arrow next to stop video, video settings. Ooh!
Then you go to my video, it should enable HD, it should be right there.
It's already enabled.
You can also touch up your appearance on the thing.
I've already got touch up my appearance marked. I've already done this.
so
And it still sucks. That's what really blows about this. And I don't know, maybe it's the camera on my computer or something, but yeah, go ahead.
it's yeah, that's probably what's quality. You can't make it better quality through sheer willpower.
That's better.
Is that better?
Yes, way better.
Way better, yeah.
Okay.
You lifted it up.
Yeah, I lifted it up.
Find a stack of Xbox or something. Find a very still cat, perhaps.
Is that okay?
Yeah.
Can you see it better?
Not really.
Not really? Come on, you gotta give me an answer.
I think it needs to be bigger. Bring it in closer, a little bit closer. Yeah.
Okay, so I gotta hold the computer in my hand and my notes in my hand and the marker and give a I can't do this, guys. Yeah, this really sucks.
Can you maybe just write slightly bigger?
Yes, I can definitely write bigger, but if I write bigger, that means I'm going to erase what goes on the board way more often. But I'll try.
Yeah. I don't know. I'm
Okay.
sorry.
Well, you know, I'm going to have to I'll restructure this for the next one. I have to kind of just figure out what's going on in this one, and then I'll try and improve things for the next one. So let's just bear with me, and yeah. Okay, well, you all know, though, that you can open up the notebooks or the PDFs of my notes, and you can see what I'm writing down.
I'm not sure the one for this lecture's up.
I mean, we can also look at the textbook thing, but I think it's kind of just a pain in the ass to have that and this side by side.
Yeah,
on
that's
one
true.
monitor.
Oh, wow, that was a loud noise.
Wow, one monitor? Yeah, a monitor. Anyways, your lecture notes aren't up yet for
Yeah.
today's lecture. This lecture is on
the textbook. And it's like verbatim.
Yeah. So, okay, I'm gonna get back to it, and I'll try and solve some of these issues by next time. Again, there's gonna be a good video of this, but you know, live, what's the point in not being able to see it if you want to do it live? Anyway, I'm gonna carry on. Okay, so it looks like we got the interaction vertex factor that we would have to write down for this thing, but it turns out this isn't quite right, because it turns out that you can't just erase a mu. A mu has dimensions, and you want to be erasing a dimensionless quantity. So when you want to erase a mu, you don't just erase a mu, but you erase h bar, square root of h bar c over 4 pi times a mu. Okay? This is what you want to erase from this. Do you see it there? Does anybody see this factor in this internal, or sorry, in this interaction term in the Lagrangian?
I don't see it.
Good, thank you. But I see people shaking their heads. That's a good response. This is a good response. Okay? So how do I erase this from this term?
You put the inverse in.
Exactly, you leave in the inverse. So if we put in square root of 4 pi over h bar c, then we have effectively erased not a mu, but square root of h bar c over 4 pi times a mu. Okay? But you can just erase the psi and the psi bar. Sorry, say it again?
Why do we want to erase that?
Because a mu, it's just a convention of units and so forth. A mu has units, and you want to only erase unitless quantities, and so you tack on this factor in front of a mu to make it dimensionless, and then you erase it.
Okay.
But again, this is something which you could derive if you were doing all this from quantum field theory perspective, but we can't do that, so I wouldn't worry too much about it. Okay, so that's the first step. You got to get the vertex factor, right? And if you think about it, these diagrams, you know, if you're doing this diagram here, the first and simplest picture might be this one. Well, this has got 4 external legs and 1 internal photon. We've got 2 vertices, so we're writing down the expression for m on this, and there's going to be a lot more rules to it, but I'm just getting the basic ones down. We have to write this factor for each of these vertices. There's 2 vertices in this. There's 2 versions of this. One is here and one is here. Okay? The next thing we have to derive is what do we write down for the internal propagator. All right? Now, in this case, the internal propagator is a photon, but we could imagine a scenario. Well, actually, I'll just add a diagram to that picture. Okay, this is a 4th order diagram because now there are 1, 2, 3, 4 vertices. But you have internal photon lines and you have internal spinor lines. This is the electron, so this is a spinor. So we need to get a propagator. We need to get expressions for propagators for both internal or virtual spinors and for virtual photons, which are gauge bosons. Okay, so there's going to be 2 of these we have to do. One of them is way easier than the other. And surprisingly, the spinor is easier. Okay, so I'll start with the spinor. All right. So for virtual electrons, or positrons actually, it doesn't matter. We start by writing down the equation of motion. So in this case, it's the Dirac equation. Okay. And I'm following the exact same steps that I followed to get the propagators in the ABC theory. I'm doing the exact same thing. So this is the Dirac equation. I'm going to rewrite it in terms of p mu and get rid of the h bars. So that's going to give me gamma mu, p mu minus mc acting on psi. Okay? And then what do I do with this term in brackets? Yeah, I want to invert it, okay? However, is this a number? What kind of quantity is this? Say it again? Well, actually, this is a scalar because gamma mu and p mu, those are contracted, so that makes this a space-time scalar.
Yeah.
So if this is a scalar and this is a scalar, this is a number, so I just do 1 over that. But it's not.
It's not dimensionless, right?
Say it again?
Doesn't it need to be dimensionless or something?
Well, no, so I'm not really worried about dimension per se. I'm asking you, is this a funny thing that is a matrix or a blah, 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 or is it just a number?
Is it because it's...
What is
is it
gamma?
because it's
What is gamma mu?
0?
Not just a number.
What is gamma mu? It's a gamma matrix. It's a matrix in what space? In spin space. So we talked about gammas early on, and now they're going to come back to haunt the living hell out of us. So brace yourself, because you're going to gammatize everything, okay? So gammas have vector indices. So the mu here takes values 0, 1, 2, and 3, but each of these are 4 by 4 matrices. So when I say that we contract that index with that index, making this a space-time scalar, it is a space-time scalar, but it's still a matrix that acts in spin space. So this thing is a matrix. In fact, if I have a matrix here and I'm subtracting a number from it, then that means I have to have the identity in spin space over here, which I could write like that. Okay? But my point is just, this is not a number, so when you want to invert it, you actually have to invert the matrix. So when I write down the inverse of this, I just want you to be aware. So here we go. What does the inverse of this look like? We want to multiply it by I, and it comes out in the following form. Okay? Now, it is not at all obvious that this expression is I times the inverse of this. But that's okay. You will get to prove that in your homework. But you know how this is. Like if I've got a matrix, M, and I want to find M inverse, I don't just do 1 over M. Because how the hell do you act on something with 1 over M? You know? So when you want to find a matrix inverse, what you want to do is you want to find another matrix. So notice here, the numerator of this is again the matrix, gamma mu. And the denominator, this is really just a number. So this thing is the inverse of this being written as, again, a matrix in spin space. And connecting this to this is non-trivial, and you'll get to do it in homework, okay? Of course, the trivial way to check it is to take this and multiply it by this, and you'll find that they give you exactly the identity in spin space. All right? So these are the steps that we did for the ABC theory, and you see we do the same steps for the Dirac, or for the QED theory. So I'm going to erase this and pop this up here so that it's on the board. And then we're going to turn to the photon, which is much harder. It's not harder, it's just kind of a pain. Okay? So, we're going to start with the same starting point. So we're going to write down the Proko equation. And if you haven't memorized these equations, that's fine. Don't worry, I don't memorize this stuff. But if I say write down the Proko equation of motion, you should be able to at least remember, okay, we wrote down the Proko Lagrangian. We varied it, set the variation to 0 to get the Proko equation of motion, and that should correspond to a bunch of derivatives acting on the field A, and if A has a mass, there should be a mass term. And here is an important observation which will pay off later. Even though photons are massless, I am going to go ahead and do this step using the massive Proko equation of motion. We'll derive it, and then at the end I'll show you what you do if it's massless, which you have to use if you're doing QED, but we need the massive form if we're going to do the weak interactions. So this is just going to solve that in one step. Okay, so first of all, let's put this in momentum space. So we're going to do the usual d mu goes to minus I over h bar p mu, and get rid of the h bars. Well, actually, I'll keep the h bars for a moment. So minus I over h bar p mu, that's just replacing that derivative. Okay? So I can multiply the i's out, and I can also notice that these will give me h bar squared here, this will give me h bar squared, and again I can get rid of all of the h bar squared terms. So if we clean this up a bit, then what we find is this becomes minus p mu a nu, plus p nu a mu, plus mc squared a nu equals 0. Okay? Now when I said this was a pain in the butt, what about this is a pain in the butt? Because, right, all I have to do is I have to take this and turn it into a thing in brackets acting on a nu, and then I just do the inverse of the thing in brackets. What's the challenge here?
They have different indices.
Yes. This is a nu, this is a nu, but this is a mu. Okay? So, hi Ross.
Hi.
You're going to want to mute your microphone until you have a question. Okay, so I've got to do a little bit of work to get this thing rewritten so that it's a thing acting on a single gauge field a nu. All right? It's not terrible, but it's just a pain. So here we go. And this is where I'm going to run out of room, but oh well. We'll just suck it up. Okay, so if I take this and I multiply by eta mu nu, or sorry, eta nu lambda, or eta lambda nu. Okay. then I can come in and I can do the following. I can say, okay, this is p mu, so that's p squared. And then I'm going to take this term and I'm going to go ahead and pull it over here because these two terms already have a nu in them. So this is going to be plus mc squared times a nu. And then what's going to be left is eta lambda nu times this guy. Okay. Now this guy, if I just act with the metric and bring down the nu here and make it into a lambda, this is just going to be p mu, p lambda, a mu. And now I'm going to hide this, and I want you to notice mu is summed over, right? You see that? So I can call mu whatever the hell I want. So why don't I call it nu? All right? Well, now we're back to where we want to be because we have an overall a nu, we have an overall a nu. So what ends up going into the brackets is the following. Eta lambda nu minus p squared plus mc squared plus p nu, p lambda is all acting on a nu. And it equals 0. Looks pretty good, doesn't it? So just to clean it up a bit, I know I don't like lambdas, I prefer mu's, so I'm going to replace lambda with a mu, which you can do because it's just one index. It's not summed over anything, so say it again?
MC squared, is the squared supposed to be outside of the bracket?
Oh, sorry, yeah. Thank you. Okay, so all we have to do is take the inverse of this and multiply it by I. Sounds pretty easy, doesn't it? No. Exactly. These are matrices in space-time. And so is this. Okay? So I'm just going to write down the answer and I'll let you work on it in the homework. So getting rid of all of this to make some room.
Should we have a closing parenthesis after the mc squared?
Yeah. Thank you. Notice this is a term that overall has indices lower mu nu, and this too is a term with overall indices lower mu nu. So these two things you can add together. So that's perfectly legitimate. Okay, so here we go. If you have a massive gauge boson, you've got to keep this term in here, and then this becomes minus I over p squared minus mc squared times eta mu nu minus p nu over mc squared. Okay? So if you have mass being non-zero, then you want to take the inverse of what's in the brackets here and multiply it by I, and that's the result. Right? It's not obvious that that's the result, but you can, again, you can prove it by taking this and multiplying it by this and showing that it gives you the identity in a space-time matrix. Okay? For m equals 0, we could just take m equals 0 in this and do the inverse. But let me ask you a question. If I take m equals 0 in the Proko equation, does the result fully describe the massless vector boson, A mu? Is there anything else that's different between the massive and the massless case of that thing, besides just that the mass is 0 or not? Feel free to unmute yourself and answer.
Me?
Whoever.
I was thinking that one difference is that in the Proko equation, the for divergence of the field A mu is necessarily 0, so P mu A mu is 0 for the Proko equation, but not necessarily for a massless boson.
So actually, P mu A mu is going to be 0 for the massless gauge boson, because that's the one. So I don't know if you remember this discussion, but we talked about the Wigner classification thing, where if you have a massive particle, then you go to the rest frame of the particle, and it turns out that you're finding the degrees of freedom in terms of the rotations around a point, which is the SO3 group. But if you have a massless particle, you can't go to its rest frame. So the best you can do is you can align its momentum along some spatial axis and then ask, what transformations can I do that leave that momentum invariant? And that turns out to be SO2. And these are reflected in the fact that if you have a photon that's massive, it has 3 polarizations, whereas if you have a photon which is massless, it only has 2. And one way to impose that is to, impose P nu A nu equals 0. But if P nu A nu is equal to 0, this term right here vanishes. The m goes to 0. And so, of course, all we're left with in this case is this. All right? Okay, so we have a propagator for an internal gauge boson, and we have a propagator, well, we have a propagator for an internal massive gauge boson, and then we have propagators for internal fermions. Okay, and then we also have our vertex factors. All right. Now, these are the essential ingredients that we need to start with, but it turns out for QED there's quite a few other things that we have to bring into the story. And what I'm going to do now is I'm basically going to list a lot of other things that are part of the story. And then in our next lecture, we'll actually start bringing them together and writing down the expressions for M, because there's a little bit more that we have to be careful about in doing that. So I'm going to just give you basically a table of useful expressions, and then we'll end there today, and we'll pick up fleshing this out next time. So, it's terrible. Okay. So, So I'm going to give you some information that's very useful for charged leptons. These are electrons, muons, and tauons. You can certainly extend QED to quarks because quarks carry electric charge. However, one important thing to remember about quarks is that they carry fractional electric charge. So there's a little bit of a difference that you have to do when you're dealing with quarks, and we'll talk about that later. So for now, I'm just going to apply QED to the charged leptons. And by the way, I mean, QED applied to an electron is largely the most common thing that we use quantum field theory to describe, because obviously electrons are the most common leptons. Okay, so in working with the ABC theory, one of the things that was important is that since everything was a scalar, we never had to worry about the order in which we wrote things. So if you regress back to what I was, the calculations for M that we were doing last time, where, you know, if you were evaluating a diagram like this, then I said you put down a factor of minus IG for each vertex, so that's squared. You put in a factor for the propagator C and that propagator was I over that. And then you do a delta function for the vertices. Where this is just a delta function guaranteeing that the total momentum coming into this one is the same as the momentum coming out, and another one for this one. And then you have to, you know, put in a measure of integration for the internal momentum Q. And then you integrate over that. I never worried about the order I wrote these things in. All I said was I got to put the integral sign all the way to the left, and I got to put the measure all the way to the right, but the stuff in between, who cares? The glory of that is that it's fine, because all of this stuff is scalar. You can move it around. You don't have to worry about shit. Do you think that's the case with spinors? Hell no. No, it's not the case with spinors. It's not the case with vectors either, although the case with vectors is a little bit easier because we're using index notation. So when a mu appears, it's appearing as a vector because of that index. And what we know by using index notation, where you sum things with the Einstein summation convention, is you can move things around. The only time you can't move things around is when you give up the index notation and you use matrices or vectors or dual vectors to represent these. Then you've got to be careful. You know, you've got to have a matrix times a vector. You can't have a vector times a matrix. However, we're not using indices for spinors. We're using matrices and, you know, these spinor vectors and spinor dual vectors. So with spinors, it becomes an issue. You have to be very careful and get things in the correct order. And this is going to be the task of creating what I love to call, which we'll learn it next time. But this is admission of the fact that I can't spell worth a crap. Spinor sandwiches. I know. And I'm going to spell it with an H there this time as well, because which one is right? Ha! What? Yeah! Okay, anyway. All right, but we're going to learn about that next time. But again, it's going to be a real headache in writing down expressions for M in the Dirac case, because we're going to have to be careful to get everything in the right order. So more on that next time. Right now, I'm just going to give you a list of ingredients. Okay, here we go. Okay, so there's another problem. There's another, and I just want to motivate some of the stuff I'm going to write on the board, because you're not going to be able to use this until next time. So one of the things about using the scalars is that if I have a scalar field and I have an excitation which is moving, that's a bump in the field, okay? And it's moving with some form momentum in that direction, okay? Now, I know the mass of this, okay? And I know it's moving in that direction with momentum. Is there anything else I have to tell you about this scalar field? Are there any other degrees of freedom associated with it which I have to specify? Shake your head or nod your head? No? Yeah, that's right. No, there's nothing else you have to specify. It's like I've got a spherical ball and it's moving that way with some speed. What the hell else is there to tell you? Okay? Now though, I've got a Frisbee. And the Frisbee is moving that way with a certain speed. What else do I need to tell you to give you all the information?
Rotation.
Well, the rotation, but more importantly, the orientation of the Frisbee. Is it flat like this, or is it flat like this, or is it, what is it? Okay? So the orientation of things which have that extra geometrical feature is something we have to deal with. Now, do vectors have a geometrical feature over and above scalars? Yes, they point in a direction. They're a vector. What about spinors? Spinors do too. Okay? So it turns out that part of our story is going to be trying to figure out what to do with the orientation of spin or of the polarization of a photon. And it turns out that in calculating m squared, we must, first of all, average over incoming spin states. Okay? We average over the incoming spin states because it's very hard to control the spin of the particles that you're shooting into some, interaction. So you say, I'm just going to throw them in there no matter what their spin is. And so that means that I should average over all of the possible incoming spin states. And this average is going to be a very important and challenging part of the story next time. The second thing, though, is what do we do with the particles that are coming out? And for particles that are coming out, we want to sum over the outcoming spin. And that's to say we're going to measure the things that come out, but we're not going to pay attention to whether they're spin up or spin down or spin anything. We just want to know how many are coming out. All right? So we want to average over the spin states of the particles that are going in, and we want to just sum over the spin states that are coming out. And we will learn exactly how to do this next time. I'm just kind of giving you this as an ingredient because I'm about to write down spinners. We need them in order to do this. Okay? So here we go. I'm going to make a chart. Useful expressions. And then I'm going to write down the corresponding quantity for the electron, or the muon, or the tauon. The other leptons, the other charged leptons, just have larger mass, so they behave exactly like an electron. I'm going to write down the corresponding expression for an anti-electron, which of course we call a positron, and then I'll write down the corresponding expression for a photon. Okay? So it's going to turn out that we need expressions for the wave functions. So for an electron, we can write, and this is just a solution to the Dirac equation. That's all it is. Okay? And these are free particle solutions, because remember, when you want to specify what's coming in and what's going out, you're treating these like free particles. And then it's when you connect the bits of this with all kinds of pictures inside that you're actually dealing with interactions. Okay? So these are going to be useful for specifying the external free particle states coming in and going out. And then we're going to have to average over the incoming and sum over the outgoing. So this is A e to the minus I over P, or sorry, minus I over H bar P dot X times U S P. And I'll remind you what this is in a moment. But this guy right here, this exponential term, that's just propagating it along. That's basically the heart and soul of the Klein-Gordon version of this, because this thing can have some form momentum. And this part right here, sorry, is the spin part. So U is the actual spin vector, or it's the spinner. But remember that spinors in relativistic theories depend on momentum. And I'm going to remind you what these spinor solutions are in a few minutes. Okay? Then if we want to do the positron, I have to give myself a little bit more room. Then psi of x for the positron we can write as A e to the I over H bar P dot x. This is how we identified the antiparticle. Okay, it evolves with the opposite sign in the exponential. And then we're going to give these spinors for the spinors for positrons a different label V. Okay? So if you've got, let me just show you what I mean. If I've got a diagram here, and I've got an arrow that way and an arrow that way, and again, we'll do this in detail next time. So time goes this way. So anytime the arrow, these are not momentum arrows, by the way. Momentum labels you put outside. Okay? And they always point in the positive t direction. These are actual particle labels, and this is saying this is an electron, and this is an anti-electron or a positron. Okay? Everybody on board with that? So when I'm writing down this M, I'll have to write down a contribution from this incoming electron of this form and a contribution from this incoming positron of this form. And I'm just making sure that I use U and V because I don't want to get them mixed up. All right, so then for a photon, we have a solution to the Proko equation, which takes the form A e to the minus I over H bar P dot X times epsilon mu of S, where S in this case just takes the values 1 and 2. And all that S means is that when you have a photon, it's got to be polarized transverse to its momentum, and you can only identify it through the Wigner classification system, which you can't take it at rest, so you're only using the SO2, which basically is rotations around that, and we can basically take two directions, and we can call this S equals 1 and S equals 2, and that's what these two labels are. Okay. So it's saying, am I doing transverse up or transverse out of the board? But there's nothing along the direction in which it's moving. Okay. All right, so we need equations of motion in momentum space. And these are pretty easy. Gamma mu p mu minus mc times u, because this is just an overall constant. Okay? So well, it's actually, sorry, it's trivial in the spin space, and this is non-trivial in the spin space. So you can actually pull this thing out of the psi expression, and you can erase it because this thing is equal to 0. And then we have the corresponding conjugate equation for the V's. All right. And then for the photon, we have that P mu, epsilon mu, P mu, equals 0, and we're going to take the gauge condition that epsilon 0 is equal to 0. Okay? So a lot of this will make sense when we start applying it. I just want to get this all out there so that we can start calculating things when we meet next time. We're going to need an adjoint for these fields. You might or might not remember how to do an adjoint for a spinner, but we take U dagger times gamma 0, okay? And we made an argument for why gamma 0 had to be part of the definition of the adjoint, and then of course that's complex conjugation and transpose. V bar is of course V dagger gamma 0, and then epsilon mu, we just complex conjugate. We're going to need an adjoint equation of motion. Again in momentum space, so this time it's going to be U bar gamma mu, P mu minus MC equals 0. V bar gamma mu, P mu plus MC equals 0. And then P mu epsilon mu star equals 0. Now the next two things that I'm going to write down are very, very convenient to work with, especially when we're averaging over and summing over spin states. So first of all, we have an orthonormality. Of the different polarizations. So first of all, if I take a adjoint spinner with spin S and the original spinner with spin S prime, then we have an orthonormality relation. So this is 2mc times the delta function of S and S prime. Okay? So if I ever encounter the combination of U bar U and these spins are different, this is 0, but if the spins are the same, then it's just 2mc. Okay? That's what an orthonormality condition usually expresses. And then we have V bar S, V S prime. In this case, it's minus 2mc times delta S S prime. Okay? And then for the photons, obviously we don't have a 2mc for the photons, we just have the delta function. And then last but not least is a completeness relation. And the completeness relation for the spinners says, if I take a spinner and its adjoint, and I sum over all the possible spin states for each of these, then this just gives me gamma mu, P mu, plus MC. Okay? And then similarly, for the adjoint, or for the anti-particle spinners, and then last but not least for the photons, Okay, so it's 5 minutes past when we should have ended. So I don't think I'm going to write up the spinor solutions. So that's what is the expression for u of p, what is the expression for v of p. I'll just include them in the notes. It'll just be a lot of writing on the board. Be aware the spinor solutions are now a little bit different than the spinor solutions that I gave you before, because when we swapped conventions, that changed some of the signs and the coefficients that appear in the Dirac equation, so the solutions are going to be slightly different, but they roughly take the same form. Okay? When we come back next time, we're going to take all this and put it together. All right, so we're actually going to draw a Feynman diagram, and we're going to put all of the steps into it, not only writing down an integral expression for it, but going through the averaging over the incoming spin states and summing over the outgoing spin states. And that's what a lot of this is useful for. Okay, so that's going to be a kind of a headache, but it's an important and required headache for dealing with QED. Are there any questions? You guys are so quiet, it's ridiculous. You got your mutes on, always. You don't need it on anymore, we're done.
We can be real loud if you want.
Yeah, you can be real loud. It makes me feel, I hear geese clucking around. I'm like, dang, man, it's just a bunch of geese.
I'm just talking, that's why I'm muted.
Yeah.
Are there office hours before the next homework is due?
Yeah, so I will have, office hours tomorrow night, and I'll probably do them between like 5 and 8 o'clock or something like that. I don't know. I mean, if you guys get on, so I'll zoom it up, and I'll be here and I'll have this board to write on or whatever, but I don't think your homework is that challenging, but it will be a refresher of the ABC version.
And it's due this Thursday, right?
Yeah, it's due this Thursday, and we are going to have a homework quiz.
How's that going to work? I know I read your email, you were kind of going back and forth between scanning and submitting that.
Yeah, so I'm basically going to make it available on the course website probably about 5 minutes before class starts. And then you'll get to work on it for about 15 minutes, and then I'm going to start lecturing. And if you keep working on it, you're a jackass. Especially if you don't show me your video. But anyway, but I don't want you to try and scan it and send it to Levi during class. Just when class is over, take your quiz, scan it, and send it to Levi. And don't take 2 hours to do so. Is there anybody who has an issue with either, you can either scan it or you can just take a picture of it and email the picture to Levi. But send these things to Levi, don't send them to me. Does anybody have an issue with doing this?
All of my notes will be taken on toilet paper.
Well, as long as it's...
I'll have to turn it in as big strands. And I can mail it, but like...
Okay, first of all, Avery, in a toilet paper shortage, the only thing I can imagine is that's going to get a little bit more than you're writing on it at some point. Yes, I think so. And secondly, yeah, don't use toilet
What do you
paper.
think he's writing with it on?
Round 2.
Round 2. Okay. Are there any questions, or how was this for you guys? Can you really not see anything on the board?
It's just blurry.
It's blurry.
You can infer stuff from context, but it's just blurry.
I mean, this is not too bad. It's also some of the upper stuff. It's harder to see.
Like those I over H bars, it's a little hard to tell it's an I.
Okay. All right. Well, I'll see what I can do in terms of improving my picture. My computer's not that old, so I don't think it's the computer. But
Can you try shifting your camera so you can't see that door? I kind of wonder if it's just like really high contrast is like blowing it out, because you
Yeah.
can't see that bottom corner of the screen.
yeah,
So just make it see the doorway.
yeah, I can try. Yeah, hold on a second. First of all, I'm going to turn this camera off.